All right, so this is section 4.4, one of the most important sections in calculus, and it's going to talk about the fundamental theorem of calculus. Sorry about the chalk dust on my fingers. Hopefully that doesn't bother you too much. Just got out of class a few minutes ago. Okay, so the fundamental theorem of calculus, what is it talking about? Well, just as motivation or background, remember we were talking about velocity functions, and we said, if you have a velocity function from time A to time B, then you could find the distance you've traveled by finding the area under this velocity curve. We also said that if you knew the actual displacement function s of t, or distance, well, I'm not calling this a distance function, right? Because your displacement here could be positive or negative, left or right. But if I knew what my displacement function was, and this is my velocity curve, right? This means that I'm always traveling in one direction. And so then for the change in, or for the distance traveled, I could just take the distance that I am, or the position that I am at time B, minus the position I'm at time A. And so these two things are the same. And so we would say in our new notation that the integral from a to b, v of t dt, is equal to s of b minus s of a. Right? And now we're talking about it just in terms of the distance function when our velocity function is always positive, but it actually works out for more generally than that. Okay, and in fact, the more general case is the fundamental theorem. So let's look at the fundamental theorem. So remember that in this case, s of t is the antiderivative of the velocity function. Okay. All right. Oh, I've got too much chalk dust on my fingers. Okay. So the general case looks at the following. We've got, did I just mess up my camera when I did that? I did. I whacked the camera with my paper. Okay, so let f of x be continuous on the interval from a to b. So our functions are always going to be continuous just to make things easier for us. Then the integral from a to b f of x dx can be evaluated by taking the antiderivative of f evaluated at b minus the antiderivative evaluated at a. And so we'll say where f of x is any, in fact, antiderivative of little f of x. Okay. This is actually called the fundamental theorem of calculus part 2, but if you see other books, you might see this as FTC part 2. We'll look at part 1 in just a bit. This is like the computational part of the fundamental theorem. And so just as an example, if f of x equals x, then do we know how to compute an antiderivative for that? I think we did earlier. That would have to be an x squared, right? You'd have to add 1 to your exponent. And then in order for us to get a 1 here, I need to multiply 2 by something to get a 1. And so that something would be a 1/2. And so if I take the integral from a to b, x dx, that's the same thing as my f of x, my capital F here, 1/2 x squared. And then this is called an evaluation bar here, a to b. And the way that you interpret that is you take your 1/2 times your b squared minus 1/2 times your a squared. Good. And so we see that the integral of x dx is actually 1/2 b squared minus 1/2 a squared. Very good. All right. Similarly, if f of x we'll just do a simple one, is e to the x. Then the integral from a to b, e to the x dx, is just going to be e to the b minus e to the a, because that's already the antiderivative. Good. Similarly, let's do one more. What about the integral from a to b of the sine of x dx? Well, let's see, cosine of x. Let's see, is that a positive or negative cosine? If this is an antiderivative, this should be a negative, right? Because then the derivative of minus cosine will be positive sine. And then we have our AB here. So that's minus cosine of B plus cosine of A. That's minus minus cosine of A. Good. And so on. So that is the fundamental theorem of calculus. It's telling us how to compute these definite integrals using antiderivatives. By the way, the reason why we can use any antiderivative is because the difference between any two antiderivatives will just be by a constant. And so when you take if f of x has a constant in front of it, right, or if you're adding a constant, when you take f of b minus f of a, you're just going to be subtracting the constant off. And so the constant's not going to matter. And so that's why we can take any antiderivative. And so typically the antiderivative that we choose is the antiderivative where the constant is 0. Okay, good. So that's the fundamental theorem of calculus. Actually, it's part 2, but that's the one we're using in the book.